So it's a great pleasure and an honor to be here giving this lecture. So I want to talk about one aspect of this broad program of analyzing the relative strength of theorems in various areas of mathematics from the points of view of it's no way to compete with a cat from the point of view of computability theory and reverse mathematics are closely connected. And what I want to talk today about is not so much specific results and so forth as some methods, so some tools that we have for even stating some of these ways of comparing mathematical theorems in terms of their computability theoretic and proof theoretic strength. But before I do want to have at least some examples. So I'm going to have a running. Okay, so how do I go forward? Yeah, there we go. Okay, so I want to have at least some running examples through the talks to give an idea of what these things are about. And I wanted to pick something that doesn't require, me to do a bunch of definitions and also illustrates a whole lot of phenomena. So I'm going to talk about these particular versions of Ramsey's theorem. So just go through the definitions. This X bracket n here, I mean the set of n element subsets of X. I'll call them n tuples, but they're unordered n tuples. And a K coloring of the n tuples is just a map that colors each n tuple with one of K many colors. A homogeneous set for this coloring is a set for which there is some color such that every n tuple of elements of H has the same color, right? So the coloring is homogeneous on that set. And then the principal Ramsey's theorem for n tuples and K coloring. So the thing to remember, I'll try to remind. But just to remember as we go through the talk is that the superscript n is the size of the n tuples and the subscript is the number of colors. That's the thing that's going to be important. So RTNK says that every K coloring of n tuples has an infinite homogeneous set. That's a theorem. It's true. But what we want to analyze the complexity of the theorem in various senses. So some really important, still very important early work on this. Oh, yeah. So before I'll just say that we can think of this RTNK, even though it's a statement, right? It's a theorem of mathematics, but you can also think of it as a problem. You can think of that the problem is given a coloring, find me a homogeneous set. So a coloring is an instance of this problem, and an infinite homogeneous set is a solution. And when we look at it from that point of view, it's very natural, at least for computability theorists, to think how complicated are the solutions relative to the problem, the instance. And some very important early work that was done by Carl Jacques, who I'm very happy to see here on Zoom. And among several other things, one of the things that he showed is that the complexity of Ramsey's theorem goes up in this very nice way as the size of n tuples increases. Now, if you actually go to try to give a proof of Ramsey's theorem, there's several ways of doing it, but the one that looks most economical from the point of view of computability theoretic power is an inductive proof, where you use RTNK to prove RTN plus 1K and so on and so forth. But at every step of this inductive proof, it looks like you are requiring a little bit more computational power at the level roughly of the coin you're going. And it's I think a really interesting question, whether that's really necessary. Is there some way of doing it that avoids that? And what Carl really showed is that no, there is no way to avoid that. So what he showed is that starting with n equals 2, if you have a computable instance of Ramsey's theorem for n tuples and K colors, then you always get pi 0 n solutions, so solutions that at that level of the arithmetical hierarchy, but not always sigma 0 n solutions. So it goes up in the arithmetical hierarchy in this very precise way. In computability theoretic terms, it goes up one jump at a time, right? But this is a little bit more precise. And so that gives you some very interesting data, and it's very easy to state, right? We have an existing hierarchy, the arithmetical hierarchy, and we can say exactly how this changes with n as in terms of the arithmetical hierarchy. Now, what about the number of colors? Well, it turns out that if you fix, so if n equals 1, you're talking really about the infinite pigeonhole principle. I'm coloring the whole natural numbers to find the many colors. I pick just one. Obviously, you're going to have computable solutions. There's some color and pick everything in that color. But for n greater equal to 2, the complexity of solutions also increases with the number of colors. Now, the thing is, though, how do you actually state that theorem precisely? because the way it goes up is much more subtle. There's no hierarchy. It's not the arithmetical hierarchy. It's not some other hierarchy that I know. There's no particular hierarchy that I can point to say, oh yeah, they go up in the precise way. They just go up. Well, what does that even mean, right? So we want to have some kind of language to actually be able to state a theorem like this precisely. So the first of these measures of complexity that allow us to do things like that I want to talk about, it was not the chronologically or historically the first one, but the first I want to talk about that will already allow us to do this, for example, for this result of Pate's at the bottom, was one that was actually, oh yeah, before I do that, let me just say what the general kind of setup for these things is. So I want to work, later I'll talk a little bit more about working formally, but just informally think that we're working in second order arithmetic. So, you know, you have first order objects and second order objects, and really all you have is numbers and sets of numbers. But if you want to code something like, you know, strings or colorings or whatever, you know, you can code them. Finite objects being encoded as numbers, and countably infinite ones as sets of numbers. So I will talk about other objects, but you know, you can always think that what we're having is numbers, sets of numbers, lowercase letters for first order objects, second order, uppercase ones for second order ones. And just like I said that we can think of Ramsey's theorem in particular as a problem, or versions of Ramsey's theorem, there's a more general setup. And I want to focus here on a particular kind of statement, but it's one that covers it's not everything, obviously, but it covers lots and lots of interesting situations, which are these pi12 statements that I want to write in this particular form, which basically says for every x, such as some condition holds of x, there exists a y such as some condition holds of xy. So Ramsey's theorem obviously fits that, but you can think of lots of other, you know, for every kind of commutative ring, there's a maximal ideal. For every, you know, whatever, there's a whatever, that kind of thing. But I want to restrict to the situation where phi and psi are arithmetic, meaning they don't actually have any second order quantifiers. And the reason for that is because then the truth or falsity of phi of psi depend only on x and y. They don't depend on an ambient, you know, on what other sets are around. So that would be important to a lot of the results. So for now on, when I say a problem, I mean one of these pi12 problems. We can think of such a statement as a set as a problem. And an instance, of course, is that x such a phi of x holds, and a solution is a y such a psi of x y holds, right? So that's the idea of why I'm thinking of this as a problem. From now on, whenever I say P and Q, I mean problems of this sort. Okay, so now let me talk about this first notion that I want to introduce here. And this one is actually due to Namir, and is a notion called computable reducibility. So I've got a lot of words there. Ignore the words. I'm going to draw a picture, which is better. So here's the situation. We're trying to reduce P to Q. So the idea is, I want to prove to you that if you can solve Q, then you can solve Q. So think of this as a two-player game where I am trying to convince you of the reduction, and you're trying to challenge me. And in this, so you're going to play first because you're going to give me some instance to solve, right? So you play first. So you're blue and I'm red. So what do? So you have these two problems, P and Q. So the first thing is you play, sorry, am I doing this the other way around? Yeah, sorry, you're red and I'm blue. That's the way I'm doing it. So you play an instance X of P. So probably what you're going to do is you're going to play a very difficult instance, right, of some sort. Now, what do I have to do? Now, this is a computable reduction. And what makes it a computable reduction is that I then have to produce computably an instance x hat of Q. That is the one that I'm going to say, if you can solve that one, then I can solve mine, maybe the one you propose. So I'm going to do that. Then the next move, what you have to do is you have to give me a solution of x hat. Now, you don't have to be computable in any way. You just have to give me a solution. So presumably, what you're going to do is you're going to give me the weakest, most useless solution you can think of. And then I should be able to, using that data, both the x and the y, I mean, the original problem, of course, but in particular using your solution y hat, I should be able to then computably obtain a solution y to my original problem. So the arrows are computable, right? So that's what makes a computable reduction. I can computably find an instance of Q, such that from any solution of that, I can then computably produce an instance of B. So I think it's a very reasonable notion of reduction. And what it allows us to do, among other things, is to precisely state some theorems that would be hard to state otherwise. Now, if you look at Jakish's results mentioned before, they imply, well, I mean, the fact that RT_NK reduces to RT_n plus 1 is pretty easy. It's one of those things you just kind of ignore one element of each tuple. It's a very easy reduction. The fact that these are proper, that RT1K properly reduces to RT2K, properly reduces, et cetera, that follows from Karl's results because you go up one level of the arithmetical hierarchy every time. But I will admit that if you state it this way, you're just basically restating Karl's result in a less useful way, right? I mean, this is like, his result gives us more data than this, right? It kind of looks neat, but that's a better statement. But then if you look at the one about colors, the one that the complexity also go up about colors, as I said, I have no like good way to state it without this. But with this reducibility, Patet's result becomes a precise result, which is that if n is at least 2, as you go up in the number of colors, RTN2, RTN3, et cetera, you also go up strictly in terms of computable reducibility. So that gives us a nice way to state it, even though I can't pinpoint some hierarchy that they go up, right? It's just they go up. So that's I think already an interesting thing that we can state results like. Okay, now if you look at this as this reduction, I mean, I think it's a very reasonable one as a notion of reduction, but you can look at it, you can see there's a few things that you might, quibble a bit and think about how you might change this to other notions. And one of them is the lack of uniformity. Like I was kind of sweeping this under the rug, right? But when I say, oh yeah, if you can solve Q, I can solve P, and you say, okay, solve this instance X, and I say, okay, I can compute an X hat, such a bit, and you say, okay, how do you compute the X hat? Oh, that's private. I'm not going to tell you, right? It's sort of like, and in fact, if you give me different X's, I might compute them in different ways, right? That seems like an odd reduction, right? There is a computable thing. You probably want to say, no, there is an actual way of finding this X hat from X, right? And so you might want a uniform version of that, where the X hat has to be obtained computably uniformly, that is by a fixed algorithm from X, and same thing for the solutions. As it turns out, that notion had already existed well before computable reducibility, and it is the notion of Weierarch reducibility. Again, lots of words, but I'll draw the picture. So as it turns out, Weierarch reducibility was introduced in the 90s by Klaus Weierarch in the context of computable analysis. And if you've ever seen it, it looks a lot more complicated than this, actually. It has these realizers and so forth. This is a special case of it that is much easier to deal with, but it is the same idea, except in this special case. And it had been, in fact, used for a while by a few people in that area to analyze problems in exactly this way. And then some of us, people started, like Demir introduced computable reducibility, people started working on Demir and some of his co-authors, and then later Karl and I started looking at the uniform version. We called it uniform reducibility. Then we realized, okay, this thing already exists. This whole community is working with this. Okay, we switched their terminology, is why we call it Weierarch reducibility. And so here's the idea. The idea is it's still the same game. Everything looks the same, except that I no longer play my game. What I do is at the beginning, before we even start, I will play 2 reductions, phi and psi, right? So Turing functionals, right? And I'll tell you what they are, right? And then when you play your X, I will not play anything. I will just give the X hat that phi produces from X. Then when you give any solution Y hat, then psi will then use that Y hat plus the original data to get you the solution Y, right? And that has to work, and that's the notion of reduction. So it's sort of, instead of playing the chess game, I say, okay, here's this computer I pre-programmed, right? It will play for me. So that's the idea of this uniform reduction. Now, one thing to keep in mind here is that obviously this is computability theoretic, right? We're talking about Turing functionals, so computable procedures. But one thing to remember is that Turing, the map that a Turing function represents, right, maps from sets to set. If you think in terms of the natural topology on Cantor space, on the space of all subsets of natural numbers, it's continuous. And indeed, in fact, like computability is like-face version of continuity, right? Or continuity is both-face computability. Every continuous functional is a Turing functional relative to some oracle, right? So in fact, there is that continuity aspect too. So Weierarch reducibility combines computability aspects and also topological aspects. So there are certain things that fail to be Weierarch reducible, not exactly because of computable failures, but because of failures of uniformity, which are failures of continuity. So that explains why there's certain things that you look at and say, well, this should be like computably do it, say, yeah, but not uniformly, right? So that's the thing. For example, so I already mentioned the result that this RTN2 is strictly below RTN3, strictly below RTN4, et cetera, computably, that was due to Pate. That result, of course, only started working for n greater equal to 2. So the interesting thing about this theorem here that showed up in various places around the same time is that it works for n equals 1 as well. So that's the interesting case. That even for that like silly infinite pigeonhole principle, right, where you color the natural numbers with finely many colors, even then, you can still get a result that you go strictly up in wire reproducible terms. So obviously, this is not exactly computability theoretic, it's more topological. So we already see that we can get some interesting data that was completely invisible, right, when we didn't look at the uniform notion over here. And obviously, there's a lot more, but I want to focus on these examples. So those are two notions that have been well studied, and there's lots of interesting results. But now I want to go back. So if we go back, well, I won't go back in some, but if we go back and think about computable reducibility, I said that there's a couple of things about it that one might quibble at or try to come up with other versions for. And one of them was this lack of uniformity. The other one was this insistence that we use only one instance of Q to solve one instance of P. Right? In general, if I say I can reduce P to Q, and you say, okay, how do you do it? I'd say, well, I apply this instance to Q, and then I apply this one, and I got it. Normally, you're not going to say, no, that's not a reduction, right? You only get to use it once. No, of course, I get to use it twice, right? And it still fits our notion of what a reduction might mean. If you're thinking in terms of computability theory, you might think of the difference between M reduction and Turing reduction. So what about getting that notion of computable reduction and allowing multiple uses? Well, as it turns out, that goes back even further than either of those notions. That is something that people have looked at for a long time. It is very connected, as we'll see in a bit, to reverse mathematics, which I haven't gotten yet, but we can look at this in this purely computability theoretic terms. Think of the notion of a Turing ideal. So a Turing ideal is just a non-empty collection of sets of natural numbers that has a closure property that if you have finely many elements in there and using those as oracles, you can compute some other A, then that A should be in there. So it's closed under computable procedures. You can think of a Turing ideal as a context for computable mathematics, right? Computable procedures can be carried out in the Turing ideal. And so that leads naturally to, well, it says we can think of a Turing ideal as a context for computable mathematics. It leads naturally to the notion of implication. Well, first to the notion of a problem holding an ideal in an ideal, and that's the obvious notion. A problem of this sort holds an I if for every X in I, there is a Y in I with the right conditions. And notice that because phi and psi are supposed to be arithmetic, remember, right? They don't change their meaning inside the ideal, right? They mean what they mean. So this makes sense. And then, of course, we want to say that P is reducible in the sense that we're going to call it omega reducible for reasons that become clear in a second. We say that P is omega reducible to Q, written P this way, P is omega reducible to Q, if P holds in every Turing ideal in which Q holds. Right? So in every context for computable mathematics in which we can solve Q, we can also solve P. And so because obviously this is like a whole context where we can do repeated computable operations and still remain inside the ideal, this is a notion of P reducing to Q where we in some sense get to use Q multiple times. And as I said, it's been around for a while. So for any of these, so in particular for omega, let me write the equivalent here just to mean that P is omega reduced by Q and Q is omega reduced by P. And for any other of these reducibilities, I'll write it the same way. So for example, if you fix n and look at different numbers of colors, j and k, you're always going to get omega equivalence. Remember, the result of Pate said that in terms of computable reducibility, you went strictly up as the number of colors increases. But here you get the same. So why? Well, so because, for example, suppose that I can do Ramsey's theorem for n for 2 colors, and you want to do it for 4 colors. What do? Well, you give me a 4 coloring. Their colors are 0, 1, 2, and 3. Think of 0, 1 as one color, 2 and 3 as a second color. Apply Ramsey's theorem for pairs. Now for 2 colors. You either get something that's homogeneous to the color 0, 1 or 2, 3. Let's say 0, 1. Now you've got 2 colors. Apply it again. Now you've got 1 color. Right? So you can do it, but you need 2 applications, right? But omega reducibility allows 2 applications that if you wanted to do RT 8 colors, you can do it with 3 applications and so on and so forth. Now, much more interesting theorem, or collection of theorems here, is that if you have m and n that are at least 3, then RTMK is omega equivalent to RTMK. So the Ramsey's theorem for m tuples and n tuples are equivalent in this sense. And that actually also comes from results of Carl, the ones I mentioned, and some other things in his paper, that you can kind of, once you reach 3 triples, you can encode the Turing jump, and then once you encode the Turing jump, if you get to use it several times, you can get as many jumps as you want, and that allows you to get any of the RT. So it's like, it's basically straight out of Jakish's work. But interestingly, it doesn't work the same for 2. Now, obviously 1, right? RT1K is obviously weak. It's going to have computable solutions. And in fact, there was one paper that I know of before Jakish's work on Ramsey's theorem. That was a paper of Specker's, in which he showed that RT22 already doesn't have computable solutions, right? So that gives the first, Carl's results are stronger, but that gives us already the first one. What's very interesting here is that RT2K is not above RT3K. So there is an there is an ideal in which RT2K holds, but RT3K does not. And that is a result, very big result at the time of Cedepun's. That was published in a paper of Cedepun's and Sleiman. So that's actually it's actually a difficult construction, but it's true. So there's some really interesting things. And notice that we already had seen that RT2K is computably below RT3K, but this is a much, much stronger result. The fact that it's omega strictly below, right? There's no amount of applications of Ramsey's theorem for pairs that you can use to get Ramsey's theorem for triples. So this allows a very fine and nuanced analysis of these principles. But 2 things. But first of all, I'm kind of saying that omega reducibility is the reducibility that allows us to use multiple instances of Q to solve P, but that's kind of seems a little bit hazy, right? How we're actually using them and so forth. So there may be a way to make them more precise. And the other thing is we seem to be like, we're missing one thing, right? We have computable reducibility, which is non-uniform and only allows us to use one principle to solve one principle. We have wire reducibility, which is uniform and only allows us to use one principle to solve one principle. This reducibility, omega reducibility, which allows us to use multiple instances, but is non-uniform. So of course, there's a missing thing in the square there, which is a reducibility that is uniform but allows for multiple instances. So to solve both of these issues, I want to talk about a notion of reduction game that goes back to a paper of mine with Carl. And these reduction games are 2-player games for reducing P to Q. I already kind of talked about computable reducibility and wire reducibility as a game. So these are like that, except now these games are going to have more than just 2 moves, right? So these are all 2-player games for reducing P to Q. Before I introduce them, just a little bit of background. The general idea is that player 1, which is the challenging player, will play a P instance. Then player 2 will try to obtain a solution to this instance by asking player 1 to solve multiple Q instances, right? Not just one, or possibly not just one. And if player 2 ever plays a solution, it wins. And that's when the game ends. If the game goes on forever, player 2 never is able to produce a solution, that's when player 1 wins. And just to get rid of some coronary cases, if a player can't make a move, the opponent wins. That's part of the rules of these games. So here is the first game, our basic reduction game, for showing that Q implies P. In the first move, as I said, the challenging player, the red player, will play a instance x0 of P. Now, it is possible that it could be that this P is so simple that with this instance x0, the other player might be able to solve it immediately without even using Q. Well, sure, it's allowed to do that, right? 0 instances is a really good way to reduce. So the blue player is allowed to play an x0 computable solution to x0 if it can, right? Okay, if it can, great. But remember, the blue player has to play computably, right? So it have to be computable solution. If it can't, then it does the same thing it did in computable reducibility, which is to play an x0 computable instance of Q. Now the red player has to solve that instance, plays any solution, right? Now, in the original computable reducibility game, this is the point at which player two would have to solve the initial instance computably, right? And we just have to do it. Now, it can do that if it can. It can play a solution that's computable in both in the joint data x0 and x1, but it could also play another instance y2, except it still needs to play computably in the data provided. If it plays another instance, then player one has to play a solution to that. Now player two can either solve the initial instance or play one more solution to Q, and et cetera, et cetera. As long as the blue player keeps playing computably in the given data, the game goes on, and either the blue player at some point solves the initial instance or it never does, and that's depends on which one wins. So this is clearly a notion of reducing one problem to another using multiple instances, right? I think this one is kind of clearly that. Now, we already had a notion of that, which was omega reducibility. So now it seems like we have two notions. Fortunately, we don't, because Carl and I showed that if P is omega reducible to Q, then player two is a winning strategy. Otherwise, player one is a winning strategy. So this is not actually the notion of player two having winning strategy here is not a new notion. It's just a new characterization of omega reducibility, which makes it clear how it is a reducibility that allows us to use multiple instances of Q to solve P. Okay. So that's one thing. So that in itself, I think, is of some interest, but not very exciting. But what we can do now is we can solve that other issue of how do we define a uniform reducibility that allows us to use multiple instances. And what we do is we play the same game, but instead of player two having to have just a winning strategy, it has to have a computable winning strategy. There's one given by a fixed functional ahead of time, just like we went from computable reducibility to wire reducibility. So now we define P to be generalized wire reducible to Q, written this way. If player two has a computable winning strategy for G, that is a particular program functional given ahead of time that plays its moves for it, right? It takes player one's move, first move, and plays the second move, takes the second move, plays the third move, et cetera, et cetera. And I should say that there is a Neumann and Pauli independently given equivalent definition to GW reducibility. Using this operator on wire reproducibility called the diamond operator. I think, yeah, I mean, it's very, I think our definition is going to work a little bit better when we move to the study of reverse mathematics, but that is there, and that is interesting. So we have this notion of generalized wire reducibility. So the way to think of it is I get to solve P for multiple instances of Q, but I have to do it uniformly, right? In a way that's given ahead of time that doesn't depend on the input. It takes the instance as an input, but the algorithm for doing it doesn't depend on the instance. For example, that thing that I said where I can solve Ramsey's theorem for four colors using two colors twice and so forth, that procedure was completely uniform, right? And so, in fact, you get GW, you get generalized wire equivalence there. So you get more than just omega equivalence. Also, remember that for omega reducibility, if M and N are at least 3, then Ramsey's theorem for M tuples and N tuples are the same. It turns out they're the same here too. Takes a little bit more work. It's still down to Carl's original proof, but what we had to do is go into that proof and see that everything is sufficiently uniform, which is not something necessarily that I would have done if it hadn't been for this motivation, right? So this actually leads us to mine certain things and proofs that were there, but have to actually be noticed and done with a little bit of care and changing some limit, whatever, to make sure that everything is uniform. So that's one, I think, good byproduct working with these things. It leads us to look at these things and seeing what proofs could, for example, be made uniform, which ones can't, and if the ones who can't, there's some other way to do it, and so forth, which might lead you to discover a new proof, et cetera, et cetera. Now, let me give another example here, which is so it's a stupid principle, but as a problem, okay, it's at least something to think about, is the ID problem, that the problem with an instance is X and a solution is X, right? Okay, it's not very interesting, but it's interesting to compare it to other things. It's the identity problem. So RT1K, Ramsey's theorem for singletons, but K colors, is of course computably reducible to that, because it always has computable solutions, but it's not wire reproducible to it. I mean, I already said that in terms of wire reproducibility, it goes strictly up from RT12 to RT13 and whatever. So it shouldn't surprise you that this is true, and this is not that difficult to show. But as it turns out, in fact, what's a little bit more difficult to show, but is that this is still true in generalized wire reproducibility. Now, this, again, this is not particularly difficult to show and should make sense, but you cannot get RT1K even with many instances of that. But the general method here can lead to more interesting results than this one if you have other principles that I don't want to spend the time to define, because the general way this works, this kind of proof works, is that RT1K is a problem that has what we call, it has diagonalization opportunity. So basically what this means is I can start giving you an instance of RT1K. For example, RT12, I can start giving you an instance of RT12 saying, okay, 0 is colored 0, 1 is colored 0, 2 is colored 0, 3 is colored 0, 4 is colored 0. And if you ever say, aha, I know what the infinite homogeneous set is, it is 0 going to, I say, from now on, everything is colored 1. You lose, right? So you can diagonalize against one opponent. ID, and many other problems that are more interesting in it, is an undiagonalizable problem in the sense that any initial segment of a potential solution actually can be extended to a solution. The actual definition is more complicated than that, but think of it that way, right? And it turns out that problems that have diagonalization opportunities can never be GW reducible to problems that are undiagonalizable. So that gives you a whole kind of class of examples. So again, you get more data out of this this notion. Another thing that you can do, once you have this game theoretic notion of reduction, is you can count, right? Because if a game ends, player 2 wins, that game ends in some number of moves, right? And so let's write this omega reduction with n in n steps. If player 2 has a winning strategy for that game, the reduction game, not a computable winning strategy, just a standard winning strategy, that wins in at most n plus 1 many moves. And similarly for GW. The reason I say n plus 1 many moves is because winning in one move is the one where you don't use any instances of Q. Winning in 2 moves, use 1 instance. So what I'm counting is the number of instances, right? Just because we started move 1 instead of move 0. So this is a notion of sort of how many instances of Q I need to do P. If I have omega there, it's non-uniformly. If I have GW, it's uniformly. So here, again, we can get a much finer gradation and a much finer analysis of these problems. For example, in this case, again, just to give this example, for the number of colors, if you change the number not for the number of colors, for the size of the tuples, we can precisely characterize if the bounds don't matter, but if M is within these bounds of N, then you can reduce M to our register from M tuples to register for N tuples in J plus 1 many steps uniformly, but you can't do it in J steps even non-uniform, right? So you get this very precise bound and you can tell exactly what's going on. For the number of colors, you get a similar kind of thing for Ramsey's theorem for singletons. So remember that the way we did this reduction from Ramsey's theorem for 4 colors to 2 colors, you use it twice, for 8 colors, you use it 3 times, and so on and so forth, right? So it seems like the number of applications is, well, I guess the number of applications is logarithmic, right? You can do exponentially much with each application. And it's an interesting question. The kind of question that I like, one kind of question that I like in inverse math is, I have a method for doing something. Is it really the optimal method, right? And we see here that for singletons, it is. Because in fact, if I'm between J to the M and J to the M plus 1, then I can do it in M plus 1 steps, but not in M steps. Interestingly, and I don't have time to go into why, but interestingly, it changes. It has something to do with computability theoretic complexity here that Ludovic Patet determined the least M such that, RTNK is reduced by RTNJ. So the same thing, but for n greater or equal to 2. And for n equals 2, it does go to infinity, but in this really complicated way. For n greater than 3, it's always 2. So you can't always do it in 1 step, but you can always do it in 2 steps with however many colors you want. So that method of doing it is not actually optimal from this point of view. And you can leverage the computability theoretic content of these theorems to actually do better in some encoding. So that is, I think, very interesting. I just want to make one more point, which is that, so we have this notion of being able to do either omega or GW reducibility in n many moves, but what that says is player two always has a winning strategy, that always wins in n moves. It is certainly possible for player two to have a winning strategy, but not one that always wins in a fixed number of moves, right? That needs more and more moves depending on the endings in the instance. So for example, we have a principle they'll just call RTN, which is just for all k, RTN k. So this, it's basically Ramsey theorem for n tuples in any number of colors. And then RT is just the full one, right? So for every n and every k, RTN k. And RT, this full Ramsey theorem, is omega reducible to RT3 too, that follows from Carl's results, as I talked about before, but you can't do it in j many steps for any j, because RT includes instances of RT4 and instances of RT5 and instances of 6, and each one of those will take mine. So you have to tell me what instance it is, and then I can tell you how long the game is going to take, right? But it goes up. Similarly, for the number of colors, RT1 is GW reducible to RT1 too, but it's not GW reducible in J for any J for similar kind of reasons. So in both the non-uniform and the uniform cases, it is possible that there's always that there is a winning strategy, but there's no fixed value, which is fine, right? I mean, computability theoretically, yeah, you can always do this with some iterates of this, but maybe I need more iterates. Okay, so I'll file this away and come back to this issue in a second. Now, let me briefly talk about reverse mathematics. So reverse mathematics is a proof theoretic program in which we work formally in second order arithmetic, which is actually a two-sorted first order language. You have the usual symbols, first order arithmetic, and you have an element of between elements of the first sort and elements of the second sort. And full second order arithmetic has, basic axioms of first order. I mean, the ones that, say that, define addition, define multiplication, that sort of thing. Then you have induction, full induction. So induction for all formulas in the language, and then you have comprehension, right? For every formula in the language, you can form the set of things that satisfy. That's a full system. In reverse mathematics, what we want to do is we want to look for weaker systems in which we can still do some theories we're interested in. So the reason for the name reverse mathematics is this idea that we have a theorem in mind, we prove it using some subsystem of second order arithmetic, and then we can try to prove the axioms of the system from the theorem. That's the reverse of usual mathematics. And then you know that those axioms are exactly what you need. You could also do the same with two theorems rather than a theorem and an axiom system, but you need to work over some base theory, right? Because otherwise nothing is going to imply anything. There's many choices, but the usual base theory of reverse mathematics is known as RCA, not for recursive comprehension axiom, computable comprehension. And what it has is it has the basic axioms of first order arithmetic, but then comprehension is reduced only to delta 0, 1 comprehension. So if you have something that's expressible both with an existential and a universal, then you can actually form the set of things that have that property. And the idea, of course, is that delta 0, 1 corresponds to computable. Computable sets are exactly the delta 0, 1 one. So this is essentially computable comprehension. Note, though, that I didn't explicitly say that, but these formulas, 5, sine, so forth, are allowed to have parameters. So this is not exactly saying computable things exist. This is saying if something exists, anything that's computable from it also exists, because you can have parameters. The reason this is a little bit different from the pure straight up computability theory, of course, is that there are non-standard models of the first order part, right? So we're not necessarily working over the standard natural numbers. We also want to limit induction. And a choice has been made. I don't want to talk about why. It's a reasonable choice, but it's not the only choice, is to limit induction to sigma 0, 1 induction. So induction just for sigma 0, 1 formulas. That makes things look kind of enough like regular mathematics to do stuff, but also is weak enough that you can get a wide variety of interesting phenomena. But you can work in weaker theories, and obviously you can work in stronger. But I'm going to fix the results that I'll mention now from now on work for a number of other systems beyond RCA, but I'm just going to stick with RCA for these definitions. Okay, so what's a model in here? Well, a model in the language of second order arithmetic has a first order part, which is a model of first order arithmetic, and a second order part, which you can think of as just subsets of the first order part. One interesting case, of course, is when the first order part is standard. It's just the standard natural numbers. And that's what we call M an omega model. And then we can just identify it with the second order part. Now, it is a well-known fact, goes back to Harvey Friedman's original work in developing reverse mathematics, that an omega model satisfies RCA not if and only if it is a Turing ideal. So that's why we call reducibility relative to Turing ideals omega reducibility, right? Because it's a reducibility relative to omega models of RCA not. This, of course, leads to a very close connection between reverse mathematics and computability theory. Essentially, working in RCA not is essentially like doing computable mathematics, except you might be working over non-standard models. So if RCA proves that Q implies P, then obviously P is omega reducibility Q, because every omega model of Q, P holds, but not always vice versa, obviously, because there are those non-standard models. For example, the full Ramsey's theorem, right, for all n and k, as we've seen, is omega reducible to RT32, but RCA not does not prove it, and that's tied to the fact that this omega reduction, the number of steps taken for player 2 to win the game is not bounded, right? It can change with different instances, and that's what leads to the non-provability in RCA. Okay. Now, this is something that we started working on in a paper with Carl, and then in a paper with Demir and Sarah Reitz's. We developed this further and made some adjustments to the games. We defined reduction games over models of RCA not. So now the idea now is the original reduction games that we had work in the standard natural numbers. But what if we work in these non-standard models, like the possibly non-standard? The notion that the notion of instance and solution of problems still makes sense over any first order structure, right? It's just something where the relevant definitions hold. Since I'm working with delta 0, 1 definability instead of computability, just as a notation, if I have these subsets of a particular first order structure n, then the n bracket x0, xn is, I just mean the first order part is n, and the second order part is everything that's delta 0, 1 definable from the given sets. So it's like closing under computability, right? Except delta 0, 1 definability to be precise. And now I can play exactly the same game that I played before, except over possibly non-standard models. So the first thing that needs to happen now, before the game even starts, we have to figure out the field of play, right? Like, what model are we working? And of course, because the ability to reduce over different models is exactly what the reduction depends on, it has to be the challenging player that picks this, right? So player 1, remember that's a challenging player, plays a model of RCA not. For technical reasons, I want the first order part to be countable, plays a model of RCA not and an instance inside that model. Now, player 2 still has to play computably, that is delta 0, 1 definably. Player 1 now does have the one additional obligation it didn't before, which is it has to play inside its model, right? Because it's determined the field of play, it'd be cheating for it to go outside the field of play is determined. So what happens now is that player 2 either solves the original instance, or plays a Q instance and has to do it delta 0 definably. So in the things that are delta 0, 1 definable in x0. And again, player 1 has to play a solution to y1, and that solution has to be in S. And then player 2, again, computably either solves the initial problem or plays a Q instance, another Q instance. Player 2 solves that one, et cetera, et cetera. Player 1 solves that one, sorry, et cetera, et cetera, et cetera, right? So it's the same game as before, except we're playing inside the model that player 1 determined. Player 2 still needs to play computably, delta 0, 1 defined. So we can define that game and see, what does that game give us? Well, the original game characterized omega reducibility. This game characterizes provability over RCA not. If RCA not proves that Q implies P, then player 2 is a winning strategy, otherwise player 1 wins, right? So this is a game characterization of provability over RCA not. Now, again, all we got here was a new characterization, except it allows us to do a few things. One of them is count, right? We can count the number of instances that it takes. And here we see a very big difference between the situation of omega models and this situation, which is that we have this compactness theorem that says that if player 2 is a winning strategy, that is, if RCA does in fact prove that Q implies P, then there's a fixed n such that player 2 has a winning strategy for the game that wins in most many moves independent of the instance. So it is not possible to have that situation where I have a winning strategy, but I have a winning strategy that in some cases takes 7 moves, in some cases takes 8, in some cases takes 9, and that goes to infinity, right? You have to have a bound. makes sense, I think, because the least n can be seen as measuring the minimum number of applications of Q needed, now improving P over RCA now, right? Because this corresponds to provability. It makes sense that that number is finite, independent of the answers, because after all, a proof is a proof, right? It's a finite object. It can only really mention Q finitely often, right? So it makes sense that we only have finite many applications. And this gives us a nice way that is not dependent on a particular proof system or your interpretation of what it means to use a principle in a proof, of the minimal number of applications of one principle needed in proving another. And as I said, we can work over other systems in RCA9, just mentioning RCA9. So the other thing we can do, of course, is we can effectivize this. We can define the notion of being generalized wire reducible to Q over RCA naught. And again, it's the same thing with the player 2 now has to have a computable, that is a delta 0, 1 definable winning strategy. And so now we have a notion, we have this new notion. That's the other thing that this allows us to do. For example, here's an example. To give more interesting examples, I would have to define a bunch of other principles, but here's one example. Suppose that you have J and K are both greater or equal to 2. Then the full RT1, so remember this is Ramsey's theorem for singletons, but and finitely many colors, but any finite number, right? This is GW equivalent to RT1J or RT1K for any J. They're all equivalent. Over RCA naught, RT1J and RT1K remain GW equivalent, and it's the same proof as before, right? If you want to do 4 colors from 2, you do it twice, it's the same proof, essentially, that same strategy will work. But Jeff Hurst has shown a while back that RCA naught does not prove RT1. In fact, RT1 is equivalent to a principle known as sigma 02 bounding, which is strictly between sigma 01 induction and sigma 02 induction. So it's not quite enough. So that tells us that, in fact, you can't, over RCA naught, you can't even win the omega game, let alone the GW. So you have that RT1 is not GW reducible over RCA naught to RT1K. So this is an example of a situation where you get the reducibility not over RCA naught, but you don't get it over RCA naught. So there's obviously, as I said, more interesting examples, but I just wanted to give one. And of course, the compactness theorem still holds in this case. We still uniformly, if we can win uniformly, there's a fixed bound that we can win uniformly by, and that's often useful. And the other thing that we can do is by restricting ourselves to one move games, then we can also define a notion of computer reducibility or wire reducibility over RCA naught using these games. So all these, and there's many other notions of reducibility that have been defined that we can now define over RCA naught and see what data and what information that gives us. So I hope I gave some idea of what these reductions are and some examples, but of course, then the game is use those to explore all kinds of different things, which have happened in a lot of papers. But here are the 2 papers that I mentioned: the one with Carl Jacobs and the one with Demir and Sarah Reitzes. And I'll leave it at that. Thank you for your attention.